The operational amplifier is the Swiss Army knife of analog circuit design. Named for the mathematical operations they are able to implement, operational amplifiers are an essential part in many different applications, like power supplies, sensor interfaces and data transmission. But before we dive headfirst into our first example on how to realize mathematical operations with electronics, we take a closer look on the basics of operational amplifiers. The symbol of an operational amplifier is a triangle, signifying that two input signals are combined to one output signal. On the left-hand side, there are the two input terminals. The one marked with a plus is the non-inverting input, while the one marked with a minus is the inverting input. The two power supply terminals are often omitted in schematics. Clearly, this symbol is just a representation, so let's have a look inside. The inside of an operational amplifier looks quite messy at first, but as the old Romans said, divide and conquer. So we divide the operational amplifier into three different stages. The input stage is located on the left-hand side and is responsible for detecting the difference between two input signals. The amplifier stage with its high voltage gain boosts the signal coming from the input stage. If you want to know more about transistor amplifiers, make sure to check out our other videos. The output stage allows the operational amplifier to source and sink large currents at its output while maintaining its output voltage. The most essential part is the differential amplifier in the input stage. Some quantities defining the performance of an operational amplifier are directly related to the incorporated differential amplifier. A differential amplifier is comprised of two coupled common emitter amplifiers and has in general two inputs and two outputs. In order to understand how a differential amplifier works, we could calculate the impact of the individual input voltages on each output. But there is a much more convenient way to investigate the behavior of differential amplifiers. Instead of the actual input voltages VE1 and VE2, we use a transformation to obtain the common mode and differential mode voltages, VCM and VD. The common mode voltage, VCM, represents the mean voltage of both inputs. The differential mode voltage, VD, is the difference between VE1 and VE2. Expressing the input voltages this way will make the upcoming analysis of the differential amplifier much easier. Also, we will use small signal modeling. This means we focus on small changes of current and voltage around a certain operating point only, rather than observing the absolute values. Let's start with the differential mode voltage VD. We assume that the potential at the emitters is constant for differential mode. This means the small signal change of Vk is 0 volts. Thus, a change in differential mode voltage results in one base emitter voltage becoming larger, while the other one becomes smaller. With the base emitter voltages, we can calculate the corresponding collector current via the transconductance Gm. These currents generate a voltage drop at the resistors connected to the collectors, which in turn changes the output voltages. These are the output voltages if the differential amplifier utilizes one output only. A full differential amplifier uses both outputs, however. The differential mode output voltage is again the difference between the two outputs. This gives the differential mode gain GD. We want the differential amplifier with a very high differential mode gain to get a strong signal out of the difference between the two input signals. The influence of the common mode voltage VCM is determined in a similar fashion. We assume that the potential at the emitters change accordingly to the common mode input voltage. This change in voltage causes a change in current through the internal resistance of the current source. Due to the same base emitter voltages, 1/2 of this current flows through each of these transistors. Similar to before, these currents changed the output voltages. This time, however, the change is the same for both outputs. This allows us to define the common mode gain GCM. A differential amplifier should have a very small common mode gain. Ideally, the common mode gain is 0, and the differential amplifier basically ignores any common mode input signals. An important characteristic for differential amplifiers is the common mode rejection ratio, or CMRR for short. The common mode rejection ratio is a measure on how well the amplifier can detect differences in input voltages while attenuating common mode signals. The higher the common mode rejection ratio, the better the amplifier. Now we know what's inside an operational amplifier. But do we have to deal with the internal structure of an operational amplifier each and every time? Fortunately not. An operational amplifier has 3 properties which are used in circuit analysis. These can be seen as rules we can apply when we are dealing with operational amplifier circuits. The first rule: an operational amplifier has a very high differential mode gain GD, which means that the slightest change of input signals can be detected. The second rule refers to the input impedance for both common and differential mode. These are very high, and in turn no currents are flowing into the inputs. The third rule states that the output impedance is very low. Thus, the operational amplifier delivers the output voltage we want him to deliver regardless of the load. Now we will apply these properties to a very common operational amplifier configuration: the negative feedback. Negative feedback means that the portion K of the output signal is applied to the inverting input. For the circuit shown, a positive voltage applied to the non-inverting input causes the differential input voltage VD to rise. The output voltage VA increases with increasing VD due to the differential gain of the amplifier. Along with the output voltage VA, the output of the feedback network K times VA rises. As the output of the feedback network is connected to the inverting input of the operational amplifier, V- increases. Thus, the voltage at the inverting input V- approaches the input voltage V+, and the differential mode voltage VD becomes smaller. This decrease in VD causes the output voltage VA to decrease again, until the circuit has reached a constant output voltage. Since the output voltage is limited by the supply voltage and the differential gain is very high according to the previously mentioned Rule 1, the differential input voltage almost equals 0 volts. This results in our new rule set for negative feedback circuits. The differential input voltage VD is 0 volts. The second rule stems directly from the previously second rule. The currents flowing through the inverting and non-inverting inputs are 0 amps. These 2 rules are all we need to solve operational amplifier circuits with negative feedback. As an example, consider this amplifier circuit. We want to know how the output voltage depends on the input voltage. We start off by applying the 2 rules from before. Now we can relate the input voltage, the differential mode voltage, and the voltage drop on resistor R2 according to loop 1. Since VD is 0 volts, the voltage drop on R2 equals the input voltage. This allows us to determine the current flowing through R2. With I- being 0 amps, the currents through both resistors are equal. We obtain the voltage drop on R1 via Ohm's law. Finally, By applying loop 2, the output voltage VA is given as the sum of VR1 and VR2. Substituting VR1 and VR2 results in the output voltage to input voltage relation we were looking for. This means the amplifier has a gain G equals 1 plus R1 over R2. By applying the two rules, any circuit involving an operation amplifier with negative feedback can be solved easily. By using components other than resistors in the circuit, more complex operations can be implemented than just a simple amplification. More operational amplifier circuits are analyzed in our next video. I'm Patrick with the Institute of Electronics. We hope you have learned something today, but anyway, thanks for watching. If you want to learn more about operational amplifier circuits, we highly recommend The Arts of Electronics by Horowitz and Hill, as well as Elektronische Schaltungstechnik by members of our institute.